All right, good morning. So today we are going to talk about lecture number 15, specifically about CNN architectures. Before that, regarding logistics, I think most of you submitted the project prompts yesterday, along with homework number 4. Quite a few of you did ask for an extension for homework 4, at least till the evening, whichever I saw, I was giving out 1 day or 2 day extensions based on how much you asked. Today morning, I saw that there were a couple more emails late night that I haven't got to yet, so I'll go back and look through that after class. Regarding project itself, the goal is for now to go through all the prompts, collate them into a single folder and give you back along with the document essentially that will list the directions that you can take for phase number 2. And we'll have more details on Wednesday. So currently, Jorge is going through the prompts in order to collate them into a folder that he can give it back to you in. So maybe on Wednesday, we'll have like a 10-15 minute discussion regarding the project itself and what phase 2 will be. Hopefully, we will start phase 2 from Wednesday onwards. All right. With that, let's go back to what we were doing last time. On last Wednesday, we started with the idea of convolutional neural networks. So if you're talking about like deep architectures, right? When we talk about deep learning, this is essentially one of the things that we discuss in deep learning, which is CNNs. And from today onwards, we'll literally dive deeper into the idea of deep learning and what essentially that means from the number of parameters perspective. One thing we did, I was not able to complete last time, was we finished the idea of convolution layers, which is essentially that you have a bunch of convolution operations that happen in a kernel-wise fashion. The reason we do this is because we know that the visual world has this kind of a stationary property, which means that there are a bunch of edges that can combine together in order to form the scene around you. There's only 3 colors, primary colors, R, G, and B, which can be combined in different ways in order to see all the colors, right? So you don't need a million set of colors in order to talk about the visual world. Just having 3 numbers, 1 for R, 1 for G, 1 for B is sufficient. So these are the kind of stationary properties that we use. We know how the world works around us, and we use that knowledge in order to create these networks. Pooling layer, we talked about 3, I believe. One was max pooling, average pooling. There's multiple other pooling layers as well. There's median pooling or many other kinds. I think what we showed was L2 pooling. But there are many ways of using pooling architectures, pooling layers. Essentially, all it does is it takes a larger set of activations of features and brings it down to a small set of features. Something like max pooling is very good because it looks at the maximum activation within your receptive field and keeps only that. So essentially, you can start thinking of your kernels right now as some templates, let's say eyes, for instance, like last time what we saw. And by using max pooling, we are keeping the activations. We are keeping the spatial region where the eyes exist. So that's one way of making sure that the invariance of features are invariant to the positional arguments that exist. The last thing that we did not look at before was fully connected layers. On Wednesday, we did not look at this. In a way, it is fine because the first 2 layers, which is the convolution layer and pooling layer, is kind of application independent. That means that it doesn't matter if you're trying to do something like segmentation or classification, you are going to use pooling layers and convolution layers. But once I tell you that the application is going to be something like classification, then you use the fully connected layers at the very end. So if I were to show you this in terms of architecture, this is what we call as AlexNet. We'll look at more about architectures today. So in this AlexNet architecture, we start off with some kind of an input, which is an image which passes through the network, which is some kind of convolution layers. And there are max pooling layers or pooling layers as well. It passes through more convolution layers, more pooling layers, before we finally get to a stage where the receptive field of your network has now looked at the entire image. Remember, each convolution layer is looking at a small part of the image. But once you start going deeper and deeper, this receptive field keeps on increasing, right? Because it's looking at the same image over and over again and combining kernels from the previous layer. So the receptive field becomes bigger and bigger. And you come to a stage where your network has now seen the entire input. based on these convolution kernels. The goal for you is now to take this layer and give a single output. Since maybe I can show in this particular slide here. So the goal here is to go from this set of convolution kernel activations to a single number, which is your output. And this number could be something like your class, right? So if you're talking about 1,000 class classification, all you need is a single number from out of it. The way you achieve this is by something called fully connected layers. And this is exactly the same as artificial neural networks that we were looking at before. When we were talking about ANNs, again, the word ANN refers to everything, but in this course, I'm just using it to differentiate from CNN. So anything with multi-layer perceptrons that we had seen before, I'm calling it an ANN, or an artificial neural network in this case. So a densely connected, fully connected layer is essentially an ANN. So I think I'd shown it in terms of this kind of graph. So let's say you have input as x1, x2, x3, x4. Your fully connected layer essentially means that there could be some number of neurons. Let me call it as, let's say we have 3 neurons, 1, 2, and 3. The goal is we will have weights that connect every single input to every single feature. So this is something that exists within this, what we would call a dense layer or a fully connected layer. If every single input connects to every single neuron, this is what is essentially called a fully connected layer. Now, again, our goal was to move away from this architecture, right? So when we started with convolution neural networks, we said that the number of parameters required to have this kind of a network is very large. It's unsustainable. And that's why we moved to a convolutional architecture. But now suddenly we are bringing this back. The reason being that we don't have that many parameters anymore. Right? Think of a normal image. So this is like a 1080p image, has 1080 multiplied by 1440, I believe, multiplied by 3 channels. This would be the number of pixels or input features if we were to use a fully connected layer across the entire image. But what we are doing is we are passing it through a network, something like this, and this number of features here is not going to be as much as the 1080 multiplied by 1440 multiplied by 3. In fact, with AlexNet architecture, I believe this is going to be something like 1024 cross 1. So essentially, we have gone down from this large number down to something like 1024 cross 1 in our using all our convolutional network. And once we have this, now we can go back to our fully connected layer and say that every single element, a neuron, must be connected to every single input to this particular layer, and we'll get an output. So that is essentially what a fully connected layer does in your entire framework. Now, depending on which library you're using, we sometimes, the way it is implemented is as a 1x1 convolutional kernel. So it's very intuitive to think about it, that instead of just connecting everything to everything else, your input to your outputs, all we are doing is convolving based on a 1x1 kernel. So instead of, before we used to see something like 3x3 kernels, 7x7 kernels, this is how we saw convolution. But if you were to do it as a 1x1 kernel, then essentially what you're doing is a fully connected layer. So the implementation of a fully connected layer is a very simple 1x1 convolution. Of course, you have to be very careful that whenever we say 1x1 convolution, we also have a 64, or the number of channels associated with it. That's a very important tidbit, that in many cases we don't explicitly state this. We always say that's a 1x1 kernel because that's the most intuitive way of looking at it, but there's always a channel number that is associated with it. So in this case, let's say 64x56x56 is the output from here. So let me say that this is 64x56x56. The way I would use a convolutional kernel in order to create a fully connected layer is basically having 1x1x64 as my kernels. Now I can have any number of these kernels. In this case, I have 32 kernels, which would imply that I get a 32 cross 56 cross 56 element layer out of this. These dimensions are very important. One question in your quiz 2 can be something like this: given these kind of input dimensions, and I could give you what the kernels are, and I could ask you what the outputs are going to be, or the inverse. I could give you the output dimensions, I could give you the input, and then ask you what the dimensions of the kernel needs to be in order to get this kind of an output. So just getting an idea of how the dimensionalities work within these layers can be very, very helpful. When implementing this within the PyTorch framework itself, I think I brought this up last time. If you just Google a very simple PyTorch implementation on MNIST dataset, you should be able to come to this particular page. PyTorch has a certain few number of examples. Again, PyTorch is the library that we will be using. Homework number 5 is going to be released sometime today, and you'll see that the entire goal of homework number 5 is going through PyTorch and trying to define these kind of layers yourselves. But there are a lot of resources out there. The most important thing that I want you to get out of this and next week's, today and Wednesday's class is the definition of all these layers. Like for instance, here, whenever we say con 2D, it's essentially what we discussed, the convolution layer. So if you go down into the forward block, as I mentioned last time, this is essentially the forward propagation. We are telling the network, this is how you need to propagate your data, right? You start off with convolution, then you start off with some kind of activation. We're using ReLU activation. We'll talk about ReLU in a little bit in today's class. And then we have a max pooling. We'll talk about dropout again. What I want you to focus on is from line 28. I can't write on the web page, unfortunately. So from line 28 onwards, this is where the fully connected layer comes into picture. The way we implement it within PyTorch is we have this layer called line number 28, which is x equals torch.flatten x comma 1. So what happens is that cuboid thing that we usually see, like this cuboid thing is flattened down into a single vector. Because at this stage, we are able to do this. Again, in the beginning, you can have a 1080 multiplied by 1440 multiplied by 3 number of pixels as your features. But when you come to this stage, it's something very small. It's like 1024, 4096. I don't remember exactly how much it is in AlexNet, but it is this kind of a much smaller number. And once you flatten it, you can think of a fully connected layer as essentially connecting every single element within this vector with the next one. And that is how you're going to define it within PyTorch as well. You have torch.flatten gives you this operation, and then self.fc1. fc1 is a fully connected layer that you're using within the framework. Of course, you can have more than one fully connected layer if you want to have a more complex operation, as we had talked about in the multi-layer perceptron before, right? You need a hidden layer in order to create a non-linear set of functions. So you can have multiple fully connected layers. In this case, we have line number 29, which is self.fc1 of x, and line number 32, which is fc2 of x. So those are the fully connected layers that can exist. There's a couple of other things here like dropout that we're going to discuss today, but essentially when we talk about the most important layers within a convolutional neural network, it refers to the convolution layer itself along with a certain activation, the pooling layer, and the fully connected layer. These are the three most important layers, or the most building block layers of a classification framework. Any questions about the layers themselves before we move on to looking at different type of architectures themselves? Yes?
Can you go back to the slide with the 32 and 64?
This one?
Why does that calculation cause it to use half?
Oh, no, it is not. So we are defining this. So it's not losing 64 from 32. If I had put this as something like 48, let's say, then this number would have been 48. So we define, whenever we define these architectures, we define the number of elements that can that should exist. Our goal is at the end of the day to come to the number 1, just one number, which is classification. So you can think of the final fully connected layer as we are trying to go down to a stage where we just get a single number out of it. I'm saying a single number, by the way, but this is actually going to be capital N, which is the number of classes.
This convolution here, does that mean that we're doing each of those 30 filters on the 64?
Yes. So when we flatten this thing, right? So we'll have x as something like this. So maybe I shouldn't do x as everything. Let me just take one element here. Just one x will be something like this. And then there will be 32 of these filters. So 32 filters. So essentially you'll have a 32 cross 1. 1 cross how much ever this number is going to be, which is given by 32 multiplied by 56 multiplied by 56. This is a bad example for showing the dimensionality itself, but essentially it's just a multiplication of everything that can exist. And it's actually in this case, it's just a 1 cross 1 cross 32 basically is the number here, right? So each filter set is 1 cross 1 cross 64. So let me actually put the same numbers here instead of devising my own numbers. So this is basically just 64 element vector, and each of it is just multiplying within the framework. So this is how you can think of it as a fully connected layer. It's a 64 element vector that is multiplying my 64 channels one by one essentially. Yes? I'll talk about ReLU in a little bit. Pooling layer, what it does is, maybe I can bring back last week's lecture. I think it's much easier shown there. So what pooling layer does, yes. So what pooling layer does is, given your entire activation function, the goal is to move from a larger dimensional matrix to a smaller dimensional matrix. Now what kind of pooling you're using will determine what the output is going to be. Let's say I'm using max pooling, which is the most commonly used pooling. Given a size 2 cross 2, which I'm going to define, I need a pooling of 2 cross 2. I'm going to look at the max element and keep that. In this case, that is going to be 9. In the next case, it is going to be 2. The next case, it's going to be 6 and 3. So the output is going to be this kind of thing. Again, the reason we do something like this is we want to think of our kernels as this templates, where if I have a kernel as an eye, for instance, I can go through the entire image and see where the maximum value is going to be, which is the autocorrelation function. And if that is the maximum, it doesn't matter if the eye is, let me use a different color than in black. It doesn't matter if the eye is here or if the eye is somewhere here, like your face is somewhere at this stage. You'll still be able to find that eye, because at the end of the day, you have taken all your elements here and you're just taking the max pooling. So it helps you detecting the fact that there is an eye in this image. So that is about max pooling, but again, there's other kinds of pooling that has different interpretations, in this case, average or L2 pooling. I'll talk about ReLU in a little bit later today when we come to a different architecture. Yes? So there are multiple, so we will be discussing until 2015 today. Still 2015, it was necessary, or I don't know if necessary is the right word. We used to use fully connected layers in order to get to a classification stage. Now you don't need that, because our computational power has increased so much that we can just have multiple convolution layers just stacked on top of it in order to get to the final state. So that is in classification. But if we are not discussing classification and we are discussing something like segmentation, it will be the opposite. You don't need fully connected layers or diffusion models or any other thing. You'll start, once you get this flattened output, you can reverse this thing. So you can go back to the input feature. Essentially, if you have seen the new DALI or Sora or all these other models, what happens is that they are giving you back the same size image, right? They're not doing classification. So it's like an inverse mapping that we do at the very end. So fully connected layer is not required, but for the purpose of this lecture, where we'll go from 1998 to 2015, fully connected layers was very much an essential part of classification networks. So that brings me to the next part of CNNs. So what we'll be discussing is example of deep CNN architectures. These are not just examples, actually. It's a very nice case study of looking through how CNNs have evolved over time and how we have come to this stage that now everything in terms of applications is all about deep learning, right? So if we let's say the artificial neural network revolution, the idea of perceptrons was there in 60s, but until the 1980s, there was no concept of something like backpropagation. So that was the first year, I believe it was 1983 or 84, where the idea of backpropagation, or the paper on backpropagation was there in Nature Communications, and after that, a few more things happened. And in 1998, this architecture called LeNet came into being. We'll start talking about this, and then hopefully by the end of the class, we'll be discussing about the last one, which is the 2015 architecture on ResNet. Through the course, of course, we'll go through other transformer architectures. Hopefully by the end of the semester, we should be able to get to those stages as well. So a couple things before we go through the architectures itself, the legend, so the way we will be defining some things. So whenever I use the words conv 3x3, or if I say something like conv 3, essentially we are looking at kernels that is 3x3. So this is how we'll be defining our convolution layers. Some kind of pooling layers, concatenation, dense layer. This is basically what we'll call a fully connected layer. Will be in these formats. And then we have activation functions. Whenever we use ReLU, for instance, we'll use R, Tanish, we'll use T. Of course, there's sigmoid activation as well, till now that we have used before, but it's not as utilized these days because we'll come to Y in a little bit as well. Some of the function, we'll talk about what batch normalization is. We have talked about what softmax is. It's a way of taking the outputs from our fully connected layer, or basically any kind of a vector, and creating a probability function. In this case, it's called a softmax. The way we would do this is, one way to do this is through a softmax function. We'll talk about what a module is going to be, but essentially whenever we talk about convolution layer, there's usually a pooling layer associated with it. So whenever we discuss these two things together, we can think of that as one module. Of course, pooling could be average pooling, global average pooling, max pooling. There are different ways. So we can think of it as module A, B, or C. And also you'll see that there's going to be a lot of repeated layers over and over again. So whenever you see this kind of a legend where module B multiplied by 2 means that you'll have module B and module B together, and going back, module B in fact refers to a conv layer and a global average pooling layer. So this is the kind of, this is more of a legend for what we'll be discussing about architectures today. So just a word on the, just a couple of sentences on the word architectures themselves. So when we say CNN architectures, the reason that this is a big thing is because, as you'll see, we don't have generally know what the best architecture is going to be, and through time, it has evolved. So in 1998, there was one kind of a way where we were doing this kind of a deep learning architectures, but by 2015, that way had completely changed. So architectures is basically us building this deep learning module based on a few layers that can that we kind of interchange and get the output. So let's look at the simplest architecture. I don't know if I should call it the simplest, but the simplest named architecture, which is called LeNet 5. This was all the way back in 1998. So let me zoom in on this portion here. So input was a 32 cross 32 cross 1. In other words, the paper that discussed LeNet architecture made it work on a data set called MNIST. Again, we have looked through MNIST many times. I don't believe that we have, I don't know if we have used it in any of the homeworks until now. But in MNIST architecture or in MNIST dataset, there's about 60,000 images of numbers, just digits, that we need to go through and classify whether they belong to classes 0 until number 9, essentially. So what was the novelty of the architecture itself? Basically, you have an input, you have a convolutional filter, you have some kind of an average pooling, you have T, which refers to the tanh nonlinearity, that is the activation function that we were using. There was an average pooling, there was another convolution layer, average pooling, and fully connected layers until you get to a stage which is number 10. Again, 10 is because this is the number of classifications that we do. I'm sorry, whenever we have used in this course capital N, that has always referred to the number of images, but in many research papers, capital N also refers to the number of classes. So to differentiate here, I'll just use the word capital C. So C is the number of classes. If I had a data set that had 20 classes, this final output would have been something like 20. If it was 50, it'll be 50. If it's 1,000, it's going to be 1,000. At the very end, S refers to my softmax classifier, which essentially is the output, the probability that I can get out of it. Now, again, this is the most standard template of a CNN. As I mentioned before, there are three important things in a CNN when it started, which was a convolution layer, check, pooling layer, check, and then fully connected layers. So all of these three things, multiple of these three things can come together in order to construct a CNN. So in this case, there are two convolution layers, there are two pooling layers, and there are three fully connected layers. All of these three things together are the LeanNet architecture. Yes? Oh, one of you.
I was going to ask, where do we usually specify this tribe?
Whenever you define within the convolution layer itself. And if it's not defined, by default, it's taken as 1. Question?
For the softmax function, is that similar to the sigmoid function?
No, softmax function is, I believe, e to the power. So sigmoid function is 1 by 1 plus e to the power of minus x, or whatever input is coming in. This is basically e to the power of something divided by sigma e to the power of something. I don't remember exactly what it is. I believe it's W transpose x plus b, W transpose x plus b. So essentially it's normalization, it's conversion into a probability distribution. I have it, I think, in the previous lecture or 2 lectures before that, what softmax function, what the exact definition of softmax function is. So it reduces the number of learned parameters and learn from raw pixels automatically. And this is very important because before neural networks, we always thought that the way any kind of processing has to be done is we extract features out of the network. And that features could be anything. In any data set that exists, we can come up with a set of features that we will decide these are the important features, feed it into a network and get the output, right? And that was basically the machine learning part of it. Learning was just a mapping from the features to the output. But neural networks, what they do is they learn from raw pixels automatically. So I can take the pixels, I can convert it into a vector and give it to the neural network without having to worry about the features myself. I don't have to extract features and give it in. Features, for instance, could be something like color. So I could say that I'm only interested in the red channel, so forget the green and the blue, and just lets me just feed in this red color. And in a way that is fine, but you are making a certain decision that maybe is not optimal. So this idea of feature extraction does not exist within neural networks. Neural networks themselves do the entire feature extraction. Yes, question?
Yeah, so is this just like a model on top? Is that like a model for what it could do, or is it only
Okay, so this was a paper called, that came out in 1998. This paper initialized the CNNs this way. So whenever we, in the next few slides, when we talk about these 5 things, AlexNet, LeanNet, VGG, it's basically these very pivotal papers, I would say, research papers that came out that define the architecture in this way. So this paper specifically said that you need Con 5 cross 5 layers. It said that we need 2 convolution layers, 2 pooling layers, and the fully connected layers. in this architectural style. So it's something that was defined by this paper here. And again, you can think of it as the architecture itself, right? You can have like 100 different floors and different configuration within the floors when you're talking about different buildings. But of course, a certain building is built in a certain way. So this architecture, so this specific neural network is built in a way where it's able to handle 10 things. Yeah. So it made hand engineering features redundant by automatically extracting features itself. It's the first popular CNN and provides a standard template, as I said. The idea of convolution layer, pooling, and fully connected layers all stacked together is LeanIt architectures. So one thing I want to talk about is the idea of top 5 error rate. Until this point, we usually think of error as top 1. So whenever we have talked about error, it has always been this idea of top 1 error rate. But sometimes top 1 error rate doesn't make too much sense. In this case, it makes sense top 1 error rate for MNIST dataset since you have only 10 classes. You cannot mistake a 5 for something like an 8. But in fact, if you actually go through the MNIST dataset, there are ways where you can, it's sometimes very hard to recognize these images just based on the fact that the way we write. I'm sure my handwriting as well, it's sometimes very hard to understand which number I'm writing, right? So in similar way, it's all based on real dataset. So what top 5 error rate does is it looks at the top 5 predictions, and if your correct answer is within those top 5 predictions, then that means you have gotten, your accuracy is going to be 1. That means you have gotten the correct answer. If I'm looking at top 3 error rate, that essentially means that I'm looking at the top 3 predictions. If your ground truth is part of that top 3 predictions, then that means I'm going to classify it as a correct classification. Again, I'll bring this back in when we talk about ImageNet, where we have 1,000 different classes, and let's say about 100 of those classes are just breeds of dogs. So, sometimes it's very, very difficult, even for human beings, to differentiate between something like a bull mastiff and a boxer. So what then would happen is that if you're looking at top 5 error rate, if your neural network in the top 5 predictions has the ground truth, which is either a bull mastiff or a boxer, then that means we are going to classify it as correctly. Again, I'll bring this idea back, but many times when you look at research papers, they report 2 things: the top 5 accuracy or top 5 error rate and the top 1 error rate. And everything that we have done in this course until this point is just the top 1. We are looking at our prediction and seeing that if it is the ground truth. If it is, then that means it's a true positive. Otherwise, we consider it as a negative prediction. So LeanIt by itself, it's a very important pivotal architecture because it's the first stackings of convolution layers, pooling layers, and fully connected layers to get your output. Question?
I was wondering, how does it automatically determine features?
So maybe that will be clearer when we talk about visualization. But when you train your neural network, what happens is that the first layers are almost always edges. The second layer are almost always this kind of a combination of edges, which would lead to these kind of corners, for instance. And the third layer after that is going to be a combination of these corners so as to give you some semantically identifiable concepts in your third layers and so on. So what is happening when you're training your neural network is you are extracting these important components within the data itself. A network has no other choice but to extract it in order to reduce its loss function. Because if it wants to learn something, it has to try to understand what the most important features within the data is going to be, extract them, and use them in this kind of stacking scenario to get your final output. It will be much clearer, that part will be much clearer when we actually start showing you what these layers look like from the point of view of either visualization or explainability. We'll talk about that later in about 2 weeks' time, I believe. So a very important part here was the unaffected by small distortions, rotations, varying position and scale, because we are using this pooling layer. That means that the receptive field and the fact that we are stacking convolutions and have a pooling layer means that there is a receptive field. It's looking at the entire image, not just a small portion of the image, and you're able to then extract. It doesn't matter where the eye is, for instance. So it's unaffected by small distortions, varying positions, scale, and all these things. It's still able to find your results. Of course, the cons is that technically speaking, it's still a very small architecture. We just have 2 convolution layers, 2 pooling layers, and 3 fully connected layers. And it's only working on this kind of a 32 cross 32 cross 1 input. These days, the kind of images we have is like very large images, right? So it doesn't work well. Just 2 layers is nowhere sufficient in order to find your outputs. Again, this was 1998, so you were limited by the amount of computational resource you had at the time. So from 98 to 2012, there was actually a very long gap. So CNNs, we knew the potential of CNNs, but we were quite limited by the architectural, the computational resources that we had. There was no GPUs technically, so it was very hard. Our GPUs were not used for deep learning architecture, so it was very hard in order to construct these models, train these models. So a lot of 1998 to 2012, the papers try to do things like sample efficiency and combine the previous way of working, like SVMs, for instance, along with neural networks, in order to find your solutions. So data sets were also small. So it's very easy to get a very good number in MNIST dataset. So top error rate was 0.95%. In other words, your accuracy was 99.05%. So there's not as much incentive for someone to work through on MNIST to show your results. So essentially, you were limited by the dataset as well. Again, since we are doing this kind of automatic feature extraction, your data must also be conducive for automatic feature extraction. If you don't have good data, then that means that it's not possible to extract features automatically as well. So dataset was a very, very important part of the evolution of CNNs. Storage capacity as well for computers. MNIST is small, but I mean, right now you're seeing that if you're doing your project, you already notice that even with your high-powered computers, SAM architecture takes a lot of space. Your data sets themselves take a lot of space. So, I mean, you're not doing the training yourself, but imagine the amount of data and the training, the computational capacity required to train that SAM module, right? I believe it was 1 billion masks, 1.1 billion masks used to train those kind of modules, the foundation modules that you're working with right now. So there was a lot of issues with that. Also, the tricks of neural network training were not established yet. We'll discuss many of these tricks. Parameter initialization, we'll talk about it. Variance of stochastic gradient descent, we've already talked about it, but we'll see again. Non-squashing activation functions, we'll look at ReLU, and then effective regularization techniques. Maybe not, in fact, we'll see one dropout today. But essentially, all of these things started coming out in the last decade from and did not exist between 1998 to 2021. The most important issue with training very deep architectures was this idea of vanishing gradient problem. So let's talk about what that vanishing gradient problem is. So sigmoid is something we discussed quite a bit in the beginning of the course, but sigmoid is not a good activation function in deep learning architectures. Even LeNet was a tanish function, right? Yeah, it's a T, which is a tanish function, and it's very similar to sigmoid, except instead of 0 and 1, it's more like 1 minus 1, I believe. So it's very similar to sigmoid in this respect. This is not a good activation function because if you look at the derivatives of what the sigmoid function is, it looks like this. So we use, let me zoom this in. So if sigmoid is the blue curve here, red curve is the derivative of sigmoid. Now remember, we always use the derivative in the gradient descent process itself. So it's very important to kind of plot it and see what it looks like. The derivatives are near 0 or going to be very less unless they're in a certain very well-defined region. So if I have a sigmoid function and I'm trying to use it to learn and backpropagate it, most of the time what is happening is that the derivative is going to be 0. So we're not learning anything at all, right? If it's near 0, if it's somewhere at this spot, let's say my output from my activation, I'm backpropagating this very small output backwards, And that number, since it's already very small, it's not learning anything. So if you remember how gradient descent was working, Wt plus 1 is equal to something like Wt plus dou L by dou W alpha. I believe this was a minus, and there's an alpha parameter. So dou L by dou W is then broken down into your activation multiplied by, the gradient of your activation function multiplied by the gradient of the parameters themselves. So this number is going to be very small. So once you try to stack a lot of layers, it's not going to learn anything. And that in entirety is called the vanishing gradient problem. Where as soon as you start using sigmoids, you cannot learn anything that is more than, let's say, 3-4 layers. And it's very hard to learn more than 3-4 layers. Now, there's many solutions to how you can go away from this. The most important one is ReLU, which is a rectified linear unit. So instead of this being our activation function, we use a more simpler approach in terms of trying to define an activation function. And it's very simple. So it's basically a max function between 0, your x, which is your input. And this is how your ReLU is defined. This is something that you saw in the hinge function as well in homework number 2, I believe, when you did SVMs as well as logistic regression with this kind of hinge loss function. So we use this as an activation function. It's a much simpler approach. As you can see, what is happening here is that anything that is less than 0 is made 0, so we're not really interested in the negative numbers, which again was true in the sigmoid as well, right? When your x is anything less than 0, it was your y or your output is still positive. It's above 0. So we are using the same principle here as well. We want everything to be above 0, but anything that is greater than 0, which is a positive, will remain the same number essentially. So that is what a rectified linear unit does. So if you look back in your sigmoid function, let's say my input x was 8, your output is going to be 1. If your input is something like 1000, your y is still going to be 1. Right? Or maybe I should not say equal to, it's close to, y is close to 1, y is also close to 1 in this case as well. So there's not much difference between 8 and 8000. Ideally, if we believe our loss function is 1000, we want a lot more changes within our parameters, right? Versus if our loss is something like 8. We need more changes in this case. But if you use a sigmoid function and try to backpropagate it, there's no difference at all between 1000 and 8. But if you use ReLU function, 8 is going to become 8. The loss 8 is backpropagated as 8, while the loss 1000 is backpropagated as 1000. So it's a much better way for learning. There's other things as well, which is residual networks and normalization. We'll talk about that when we come to those appropriate things today itself. So the next very, very important architecture is AlexNet. So this was in 2012. One of the more important contributions was in AlexNet, we use ReLUs instead of tanh or sigmoids. So helping to solve the vanishing gradient problem. There's something called dropout regularization and normalization between layers that is done. We'll discuss about that in specific slides. So this also was the first architecture that was run on GPUs. So we were able to parallelize the entire process and run it on GPUs. So this is the architecture over here. You have an input. Again, before it was just on very small 32 cross 32 pixels, right? But now these are recognizable images. It's 224 cross 224 cross 3 images. If you display it on a screen, it's very easy to see what it is. These are actual images that exist. They pass through convolution layers. By 11 cross 11, I mean the kernel size is 11 cross 11. R is a ReLU. There's max pooling, convolution of 5 cross 5, max pooling, and there's a cross times 3 here, which means that this is replicated thrice. Your 3 cross 3 convolution kernels are replicated thrice, followed by max pooling and this kind of fully connected layer. 4096 is after flattening, by the way. So you take that final cuboid and you have that flattened output as 4096. Then you have another fully connected as 4096. And this here is the number of classes. 1000 is the number of classes that it is classifying. This is very important because the data set we'll be now using is ImageNet. I have a slide about that as well. So you can clearly see that it's a deeper architecture. We have one 2, and 5 convolution layers instead of having just 2 convolution layers before. It's also more robust. It has something called data augmentation. We'll talk about data augmentation later as well. It won the ImageNet challenge and significantly outperformed the traditional methods. So I have a slide about that. We'll talk about what that means as well in a little bit. So this is the architecture itself from the paper. This is how the architecture was defined. Again, first use of ReLU, first use of norm layers, GPU implementation, and dropout. Let's talk about the one important thing, which is dropout. So we saw this here as well. If I go back to that website, yeah, dropout was an important part. So you saw dropout in line number 27. You saw dropout in line number 31. Now the question is, what is dropout? So you can start thinking of dropout as this kind of regularization framework. So this was actually a video in my slides. I forgot that when I converted to a PDF, we can't see it. I didn't bring my laptop, unfortunately, today. So maybe next time I'll bring back the slide again just to make some things clearer. But dropout is essentially this regularization mechanism where we start removing certain neurons. Neuron pathways within the neural network. So in this case, let's say that this is my architecture I am looking at, and I have a dropout layer that I'm using. Let's say in this case, how much was the dropout? It wasn't defined in this case, but let's say I have something like dropout 0.25. So you see here, so 0.2. You have 0.25 and 0.5. So let's go with the first number, which is dropout of 0.25. What that means is at every epoch, at every run of your forward propagation, 25% of your neurons are disconnected. That means I have some input here, x1 to x4. At my first run, maybe I'm using 0.25 dropout in this case. In my first run, this neuron and this neuron are going to be deactivated. That means that all the weights coming into this are going to be 0. And this is done randomly. At every single run, 25% of your neurons are going to be deactivated. That is, you won't have access to it. Your Ws are going to be 0. And you still expect a good output. You still expect a right classification in this setting. So essentially what you're doing is adding this kind of noise within the training process. And this is something that we have seen before, right? This is a basic regularization technique. Instead of right now adding noise to the loss function, we are adding noise within the network itself in order to increase the amount of regularization we can have. Again, we need regularization because regularization prevents overfitting by ensuring that there are no codependent features within your data set. So dropout makes the training process noisy. Again, the whole goal of regularization is to make a noisy process so that your training is not fit, your network is not overfit to your training data. Rather, it helps with the test data. That actually is seen here on the left-hand side. So if I were to think of the train loss and test loss, going back to the regression slides that we had, we start off with a very high loss function, but then our goal is that during training, this loss function needs to decrease, right? And you see that the train and test loss keeps on decreasing. But at a certain point, somewhere, let's say at 12.5, you'll see that without dropout, test loss starts increasing. That's because your network has now started overfitting to your training data set. And again, this is something that you might have seen in homework number 4 as well, where when you're doing your segmentation, you can get like 0.99, 0.995, all these numbers. But at that point, all you're doing is just overfitting to just that one image. You're not really learning the aspects of segmentation. So what you really need is something like this, the with dropout test loss, this one here. So this is essentially what we need. After a certain amount of time, there's not much more you can learn from your training data set. So your test data set kind of stabilizes at this stage. Your training loss will always decrease. It doesn't matter if it's how much unless you have added a huge amount of regularization. Your training loss always decreases. It's just that when there is no regularization, your training loss is going to be very steeply decreasing. increasing, versus with regularization, it's still decreasing, but not as steep as it was before. So essentially, dropout is a form of regularization that we can use within our framework. Again, this would have been much easier if I had this video. What happens is that, let me try to explain without the video itself again here. So what happens is that you're disconnecting each element within the neuron, right? So think of it as our goal is to avoid memorization. So let's say given a certain input X, if I were to traverse something like this input, so red means that is the most highly activated element. So let's say this particular kernel or this particular weight has the highest activation given a certain input X. So this will be the highest number. So let's say this will be 1, this is 0.1, 0.05, 0.2 and 0.1. All these numbers are less, but 1 is my highest, right? So that's what so the highest activation at this stage. And then let's say the highest activation in the next layer is going to be something like this. So again, this is going to be 1, this is going to be 0.1000, and the highest activation is going to be this. So this is going to be 0.86, let's say, while this is going to be 0.12 and 0.02. So you want this as your output. Your output has to be class number 3. And sometimes what happens is that since we have millions and billions of parameters in our networks, it memorizes these paths. Given a certain input X, there is a particular path that input can take in order to get to the final output as 0.86. So it's literally memorizing your data point and the path that it needs to take in order to get to that stage. But what happens in dropout is suddenly you disconnect this particular element, that you say that all weights leading into this element is going to be 0. So in that epoch, your network has no other choice but to distribute this 1 into all the other places. Right? So it needs to relearn many weights and many activations in order to say that based on the deleted neuron, I can now go back and distribute that activation among the other neurons as well. So in a way, you are now saying that this blue region is during dropout. This does not exist here. So a part of this is going to be taken by all the other neurons. So one neuron is not doing any kind of heavy lifting for a particular input. So a particular element X is being looked at by every single neuron in order to get your output. So this is essentially what dropout does. Yes? Yes. So if I'm using 0.25 as my number to define in line number 16, that means 25% in that layer. So I'm defining in the init module, I'm defining dropout with 0.25, dropout 1, so, and then I'm defining that within 27. So after the max pooling layer and before the flattening, the layer that exists over there, 25% of those neurons at every epoch is going to be deleted. Or maybe deleted is the wrong word. They'll be dropped for that particular epoch. They'll still exist within the network itself. It's just that at that epoch, nothing will be updated. Your gradient descent is not going to do anything with respect to those weights and biases. So that is about dropout itself. The next, of course, is ReLU. We talked about ReLU activation function. The idea is that your sigmoid function saturates quite quickly, unless it's in the middle of the region, which it rarely never is, because you have -infinity to infinity, your range, and you can't always expect it to be somewhere in the middle over here. So same with tanh as well. So ReLU is a much better activation function. The problem with ReLU, which we are not going to be talking about, is the fact that while it is a continuous function, it's not a differentiable function. At this point, you have a local nonlinearity. It changes from 0 to x. But what that does is that it's not differentiable at this point. If you were to construct a limit going from the left-hand side and the right-hand side, it won't merge. That is essentially what we mean by it's not differentiable. So at this point, your coming from the left, your limit versus coming from your right is going to be different. It's not differentiable. And one thing that we had mentioned before is that we're using this within a gradient descent framework. So we want it to be differentiable. But we'll usually handle this by, oops, I'm sorry. How do I... Let me put my phone as well in plane mode. Yeah, that should help. All right. So given this kind of framework, we actually saw this about differentiability in homework number 2 as well. When you were trying to implement gradient descent in the hinge loss function, in logistic regression and SVM, we had specifically said, look at it as an if-else statement. If it's less than this, then do something like this. If it's greater than this, then do this other function for your gradient. And that's very important because if you don't do it, there's no single function for differentiability. For sigmoid, it's something like sigma multiplied by 1 minus sigma, right? There is no simple equation that represents the gradients or differentiation for a ReLU function. The way we do it is by using something called subgradient. And it's very similar to the if-else statement that you wrote. Again, we won't go deeply into this. This is not an optimization course, but essentially you need to understand that that ReLU function itself, it's not trivial in order to use something like this within our framework because the gradients themselves are not differentiable. So this is actually the training error rate when we use something like ReLU versus when we use something like tanh. It's much, much faster when we are using ReLU function as our activation function. Another important factor within AlexNet was the idea of normalization. So we already know that normalization is very, very important. Like if you tried across different homeworks, normalization was very important, right? So we always do normalization on our data in the beginning before we feed it into a network. But what happens is that once we start feeding into these large architectures, you do your normalization in the first stage, but that doesn't mean that it's carried forward throughout the different layers. So what needs to happen is normalization within the network itself. In other words, we need this kind of a norm 1, norm 2 within the network itself because there might be some kind of shifts that have happened within these kind of large neural networks. So in this case, what would have happened is that let's say you start off with this kind of a covariance matrix to begin with of your data itself. By the time you come to the, I don't know, the 5th convolution layer, the covariance matrix might look something like this. So all the bells and whistles that you would have designed with the covariance matrix in mind, your Mahalanobis distance and stuff like that, is not going to work right now because of this huge difference within the covariance matrix, right? And that's why we need some kind of a regular normalization layer within our architecture. And AlexNet was the first architecture to actually, or it was the first paper to define what this normalization must look like. They called it LRN, which is local response normalization. It's given by this function here. Looks quite complicated, but it's not really that much. What is happening is we divide the output of a kernel by the output of nearest other kernels that might exist. I'll come back to this slide by showing you what that essentially means. So let's say this is our cuboid that we usually see within our activation functions. Our response of our normalization for the first element here must be dependent on all the other kernels that might or that should exist essentially. So in this case, the first one will be dependent on the second element here. Then the second element's kernel or activation must be dependent on both these elements on the adjoining sides next to it. So let's actually look from a kernel perspective. So let's say that I have certain convolution kernels. I passed an image through those kernels and I have a certain number of activations. So this is the activations. The output of that is the activations, right? So let's say I start off with 1, 2, 3. I hope you can see the blue. Yes. So 1, 2, 3, 4, 3, 6, 7, 8, 9. These are just the activations that exists. And this is from kernel number 1. K equals 1. This is from kernel number 2. This is from kernel number 3. And this is from kernel number 4. So there are 4 kernels that have acted on a particular image, and you get the output. If you do normalization, what you're going to do is based on this formula here. Your B, which is the output after normalization, is the initial element A before normalization divided by some scaling factor K plus alpha into the sigma, which is the summation, AJXY whole square in the nearest neighborhood. So in this case, all to the power of beta. So let's actually go through this example and see how we get it. Let's start by taking the simplest possible thing, which is, let's say K is equal to 0, alpha equals beta is equal to 1, and capital N, which is the number of kernels. We have K is equal to 4 here. Maybe I should have used capital N is K here. Oh no, I've used K here, so okay. So forget the usage of K. So number of kernels here is capital N, and N is 2. This N over here, N equals 2, which means that I'm just looking at the nearest neighbors, the neighbors next to my particular kernel. So for the first one here, which is 1, I would have to use B is equal to 1 divided by 0 plus 1 alpha multiplied by 1 square plus 1 square. This is the equation here. So my A was 1. K is 0 that you see here, then 1 multiplied by this 1 alpha here is 1, which I've shown here, multiplied by 1 square plus 1 square is, this is the 1 square and this is the 1 square, which gives me 0.5 as my answer to that normalization block. Maybe I'll show another one, so hopefully that must be clear, that will become clearer. The next one is 2, element 2 over here. So if I want this, the normalized part of that, it's going to be 2 divided by 0 plus 1 multiplied by 2 square plus 2 square, which is given by this 2 square and 2 square, which is 2 divided by 4 plus 4, which is 8, which gives me 0.25. Which exists here. So the leftmost kernel, every single instance of that activation is in fact given by an output of this particular formula. Any question about these two numbers here, 1 and 2, how that becomes 0.5 and 0.25? Yes?
Where does the plus 1 come from on the bottom of the 2 fraction?
This one here. So this entire denominator is 0 plus 1 into 1, because I've taken alpha equals beta equals 1. So 1 multiplied by the summation. So basically aj x comma y whole square. So in this case, I'm looking at, maybe I'll use a different color here. I'm looking at this and this and this and this. So that means it's 1 square plus 1 square. So that's just the denominator that we have. Sorry, that's just multiplication. That's my weird way of writing x, and sometimes it just becomes like this. So it's just x multiplied. Yes?
So the x and y, like the blue square is on the face of the cube, and then like the orange square is like 1.
Yes. Yeah, one next to it, basically. So each of this is one kernel. So the way this is defined is this here is k equals 1, kernel equals 1, k equals 2, this is 3, and this is 4. So we have taken this and shown it like one stacked next to each other rather than stacked behind each other. Yeah. 3 by 1, basically. It's just looking at this one. It's just that the corresponding element 1 is doing with 1. You can do what you suggested as well. That is going to be something called intra-channel LRN. While that exists, it wasn't used with AlexNet. That particular architecture, it wasn't used. So if I were to, let me erase this and do this for one of the middle kernels. So let's say I am doing for this one here. So till now, 0.5 and 0.25 were for the output of the first kernel, right? But there's another kernel as well. I need to normalize the orange outputs of the orange kernel here as well. So 1 Before we were just taking 1 square plus 1 square, the blue and orange, because it was the final, the one on the very left. But now we are looking at the middle portion here. This portion here is essentially this, right? That is what we're talking about. It needs to look at two things, this one and the one to the left and one to the right. So in this case, your 2 is going to be 2 divided by 0 plus 1 multiplied by, you're looking at this square, and this square. So 2 square plus 2 square plus 1 square. So 4 plus 4 plus 1, which is 9, and I believe that should give you like, which should I start with? 2, right? I believe that should give you like something like 0.22 as your output. Right? All you're taking is the element itself, adding the square of the element to its left, which is the 2 square here, and the square of the element to its right, which in this case is 1 square, along with itself squared, which is 2 square. Yes?
And then we talked about like, when we talked about like 3 by 3, for example,
Yeah.
would this, for example, 100 layers, 10 at a time,
Yeah.
5 to the left, 5 to the
Yeah. Then that means that here we are choosing n equals 2. But what you're saying is like, yeah, if we choose the n to be higher, so if I go back to this particular formula here, you'll see that the maximum it can be is capital N minus 1. N is the total number of kernels here. So that would be, in your example, this would be 100. So the maximum it could be is 100. And I plus n by 2, which is you're taking 10. So 5 to the right and 5 to the left, you'll be using that in order to do it. So this is all just coming from this formula. So this is a type of normalization that is called local response normalization. Given the response to your kernels, which is your activations, you're just taking you're normalizing it based on the output of these activations. So an important part here is that LRN is non-trainable. This will make more sense when I talk about batch normalization, where things are trainable. So it does this kind of a lateral inhibition scheme, which basically means that given your current activation, it goes through laterally across all the other channel outputs and makes sure that your current activation is not very high compared to all the other ones. Because you want two things, right? Even in dropout, when we talked about it, we don't want one element to be so high that it has memorized a particular input. So you want to make sure that all of them are learning together. And that is essentially what your local response normalization is giving you. And also that this output has a certain shape with respect to your, I'm showing covariance matrix here because that is what we saw in homework number 4, but you can think of it some kind of a distribution that your input had. You want to make sure that that continues throughout the network as well. So it enhances peak and dampens flat responses. It suppresses flat but high responses, which might not encode much information regarding stimuli. And of course, this helps in the generalization process. The top 1 and top 5 error rates are decreased by 1.4% and 1.2%. Now, whenever I say that the accuracy, the error rate decreased, a very important thing is this ImageNet dataset. So again, datasets are very important when we discuss these architectures. MNIST is a very simple dataset. So back in 2012, we had this thing called ILS VRC challenge, and until this point in 2012, before this 2011, we had models that was not based on deep learning. It was all deformable part models. I think that was the biggest thing at the time, SVMs and deformable part models. And the error rate then was around 26%. In other words, the dataset itself has about 1,000 classes. It's all natural images. So cars, again, the breeds of dogs, different birds. There's many, many natural classes that can exist. And there's about 1,000 that exist within this dataset. You have about 1.2 million images for training. This is an official photograph, by the way, of the dataset itself. So it shows all the different classes that can exist. It's very important that you just go through and try to understand this dataset, because again, it's a very pivotal dataset. Even till today, any image processing paper on computer vision looks at this dataset as like a benchmark to benchmark their results. It has about 1.2 million training images and about 150,000 different images for testing. And this is what you see here is the error rate. So from 26%, it went down to 16%. And this is a huge, steep drop. Before 2011, I believe it was very similar to the 26%. It wasn't as steep drop as this. So from this point onwards, everything that we started seeing was deep learning architectures. So AlexNet came out in 2012. It had a 16.4% top 5 error in this data set. And maybe the top 5 error in this makes more sense. When you have 1,000 different classes and very fine-grained difference between classes, what you can do is not just look at the best prediction. You can look at the top 5 predictions and say if the ground truth is present within the top 5 predictions, then you basically increase your true positives or you increase your accuracy. So this is the top 5 error rate, and it makes a lot more sense in something like ImageNet than it would back in like MNIST dataset. The number of testing images, I don't know if I mentioned this, is itself 150,000 images. So when we say that error rate of 16.4%, it's still substantial, right? On 150,000 images, 16.4% essentially means that there's about like 20,000 images that have been misclassified. So there's a lot more room for improvement, and that is essentially what the next few years were. Until about 2015, 2016, ResNet architectures, we still wanted to make sure that we did the best possible. This here is very important, which is the human error rate. If a large number of people were showed ImageNet dataset and they were asked to classify between the 1,000 different classes, of course, again, it's very difficult to, there are 1,000 different classes. There's very few people who know the difference between, let's say, all the breeds of dogs or all, spoonbill, flamingo, crane, and all these very fine-grained differences between birds. So many people would not know, and the average human error in classifying on the 150,000 images is 5%, average top 5 error. So what was thought in 2012 is that this is almost an unbreachable kind of error rate, that these kind of automated neural networks won't be able to perform better, which was proven untrue. Back in 2015 when ResNet came out, it did better than human beings in terms of, at least for a very specific task of classification on ImageNet dataset. So in terms of the pros and cons, AlexNet was, it used GPUs in order to do its training. It was better than feature extraction, of course, because of depth, and worked on any kind of images with multiple channels. ReLU activation function was used. But of course, it has less depth than future models and requires longer training time to achieve higher accuracy. So this was about AlexNet, which is a very, very pivotal architecture within the entire framework. Any questions about AlexNet itself? I think there's about 65 million parameters. I don't know if I mentioned this anywhere or if I have it within the slides. There's about 65 million trainable parameters within this network, and by that I mean the number of weights and biases and any other trainable thing is around 65 million in number, which again is a huge architecture. But in the cons, we write that less depth, it needs longer inlay, less depth than future models, which essentially means that even more number of parameters have been added to today's models compared to like back in 2012. Next is VGG architecture, but we'll start discussing this on Wednesday. Wednesday we'll also go through the project. I think that part is also going to be very important, and hopefully we'll finish this particular lecture on Wednesday. All right.